Hey guys, welcome back to Academy once again. So in this lecture, we are going to start our new chapter, that is reaction mechanism. And this chapter will be very important for you because in this chapter we will understand all types of mechanism possible in organic chemistry. For example, let's say we will discuss here SN1, SN2, SNI, E1, E2, SNAR, right? And whatever the mechanisms are possible, we are going to discuss in this. Fine. With their stereochemistry, and we will also discuss examples from the reference book like Claydon and Carruthers and all, right? Whatever the good books you have for the reaction mechanism, and also along with that, previous year questions will also be solved in this lecture series. So watch this lecture series completely, and I will definitely try to clear all your concept regarding this from basic to advanced level. And I think after watching this all video lecture series of this reaction mechanism, you don't need to even read reference books and all. I will try to include all the concept regarding the reaction mechanism in this. So the lecture series might be quite long, so please tolerate it right. And so let's start with the topic. So in this lecture we are going to start with the first one, which we have is nucleophilic substitution reaction. In nucleophilic substitution reaction, if I talk about the nucleophilic substitution reaction, so what happens in this, we will have a nucleophile, right? And this nucleophile substitution reaction means generally in substitution reaction means like any one atom or the group of atom will be replaced by the other one. For example, if I am taking the example of this one here, if I have this one and if we have this nucleophile and this nucleophile is going to replace this Br, so this will be a example of substitution reaction, plus Br minus will be removed over here. And this nucleophilic substitution reaction are of two types. We will also discuss about the electrophilic and in the later part, right? And so this nucleophilic substitution reaction is of two type. The first one which we have is SN1, and the second one which we have is SN2 type reaction, right? So we will discuss with this SN1 and SN2. So now let's start with the SN1 reaction. So what happens in case of SN1 reaction? First of all, generally if I talk about the SN1 reaction, so what happens, we consider a tertiary alkyl halide, and this tertiary alkyl halide might be this one which we have taken over here, and here we have one nucleophile, right? And this nucleophile, and this replace this leaving group. More precisely, if I say we have something like this, here any group is present and here we have the leaving group, and this leaving group might be, this might be Br, Cl, I, F, OTF, right? And it can have also OTS, right? OMS. So these all can be this leaving group. So these leaving groups are actually replaced by any nucleophile, right? So this is the example of nucleophilic substitution reaction, and here generally we take third degree alkyl halides, right? So that is replaced by the any nucleophile. That is the example of SN1 reaction. Now the next one, if I talk, so in here what is the criteria? Here what we have? Here we have the sp2 hybridization, right? Here this carbon is sp2 hybridized. If I talk about this carbon, so this carbon is sp2 hybridized and it is reacting with this nucleophile. Now the question is it possible to replace over here something? Your answer will be no. Why? If it nucleophile will attack over here, so this will come over here and here we will have this as O minus, and nucleophile will get added over here. So this is not example of substitution reaction, but instead it is example of addition reaction. So the first thing is, in the nucleophilic substitution reaction, in especially SN1 and SN2 if I talk, so the carbon at which the substitution will take place, that should be sp3 hybridize. It should be sp3 hybridize, right? Now let's talk some points about the SN1 and SN2. So what happens in case of SN1 and SN2? SN1 versus SN2. Here generally if I take a substrate plus here what we have? Here we have nucleophile, and it is giving a product like this, right? So if I talk about the orders, so in order of SN1, here in case of SN1, the rate is directly proportional to concentration of this substrate only. But in case of SN2, if I talk, so here the rate is directly proportional to the concentration of substrate and the concentration of nucleophile. So this is what, this is a first order reaction, and this is a second order reaction. So SN1 reactions are first order reaction and SN2 reactions are second order reactions, right? So I hope it's clear till now. Now so many things are here to discuss, and we will go step by step to understand all the things related to this reaction mechanism. And the next thing, if I talk about the SN1 reaction, so what happens in case of SN1 reaction? If I talk, so here what we have? Here we have this leaving group, and here also in case of SN1 reaction we require protic and polar solvents. And this step, the first step which we have is actually, this is RDS. RDS stands for rate determining step, right? And here the formation of carbocation will take place, and the formation of once this carbocation will take place, and here we should have a weak nucleophile. Let's say we have this OH minus, right? So now what will happen? This is going to attack over here, and the formation of this product will take place. So this will be something like this. And also, if this carbon is chiral carbon, if this is chiral carbon, so in that case, here the racemization will take place. Here the racemization will take place, right? So that is the next thing which we discuss about this one. Now, the next thing, if I talk over here, if I say regarding the substrate choice, so for SN1 we have 3-degree alkyl halides, and more precisely if I say are not alkyl halides only, but the leaving groups which we have mentioned over here, right? So these are the good leaving groups actually. Fine. And if I talk about the SN2, so it has 1 degree, right? 1 degree. Here if I talk about compound, so 1 degree alkyl substituted alkyl, and this leaving group, this leaving group substituted compound will be over here. Now the thing is, if I talk about this 2 degree, so this is moderate one. Moderate means in between, this will be in between, right? 2 degree, it is in between. It can also prefer SN1 and it can also prefer SN2. It all depends on the reaction condition, what we are doing over there, right? And the next thing, if I talk about the stereochemistry, and in the stereochemistry if I talk, so in case of SN2, what we have? In case of SN2, the inversion of configuration takes place, and in case of SN1, racemization takes place. Racemization takes place, right? So this is the basic thing regarding the SN1 and the SN2, and here we discuss about the choices of the substrate and the stereochemistry, right? So these all things we discuss. So this is just basic one, and let's begin with the a little bit about, let's know something more about this all topics, whatever we are discussing right now. Now the thing is, if I talk about the SN1 reaction, we were talking about the SN1 reaction. So in case of SN1 reaction, what I told you here, we have 3 degree any leaving group substituted compound. So generally what happens here, the formation of carbocation takes place. Now the thing is, if I talk about the formation of this carbocation, so this carbocation is actually the planar one. If I try to draw its lobes over here, if I try to make it something like this, so what happens in this case actually, so the thing is here with the substituted groups which are present over here, actually the repulsion will be more in this case, right. So that's why this prefer a planar structure like this. Here we have this carbon, right, and here one and here one and here one, something like this. So here in case of carbocations we have trigonal planar structure. Right. So this is about the stability of the carbocation. And the rate of reaction, if I talk about the rate of reaction and activation energy, rate of reaction and the activation energy, in that case what happens, it all depends on the stability of the carbocation. If the stability of carbocation, is high, then activation energy will be low. Remember this sentence, what I told you, if the stability of carbocation is high, so the activation energy will be low. And after this what happens, we have any weak nucleophile. In this case generally we prefer weak nucleophile, right. And what happens if I talk about this one compound, suppose if we have, if here I say the SN2 reaction is taking place, so is it possible? Now the thing is, if you will see over here, so what is happening here, we have the bulkier groups, right. Here we have this methyl and this methyl and this methyl. So in case of SN2 reaction, actually what happens, the nucleophile attacks from the back side. So once the nucleophile will try to attack from the back side, so in this case it is not possible to reach up to this carbon. So this is also the reason why the tertiary substituted compounds more prefer SN1 instead of SN2. So this reaction won't be possible because nucleophile cannot attack from the back side over here. So that is the one thing. And the second thing what I told about the stability of the carbocation, here it is very easy to form the carbocation, right. And this step is known as RDS, rate determining step. And the next step which we have over here, here the weak nucleophile which you can see over here, because this is a carbocation, so we don't need much strong nucleophile or the basis like substance. So this can definitely come over here and the formation of this compound can take place. Now the thing is, if I say this carbon is chiral carbon, right. If this carbon is chiral carbon, so in that case here we will have, here the racemization will take place, plus minus means both R and S type of compounds will be formed in this case, right. I hope you are getting what I am trying to say. If this carbon is chiral carbon, right, asymmetric carbon, if I say this is what, asymmetric carbon, means this carbon will be substituted by different groups, let's say L, M, N, and here we have this leaving group. So here plus minus means R and S, both configuration will be formed in this case, right. So we discuss about this one up to till now. Now the thing is, we have already discussed about the stability of the carbocation. Now if I say stability of the carbocation, so you know that 3 degree carbocations are more stable than 2 degree and then this 1 degree. So definitely here the activation energy will be low and this will prefer to form the carbocation. And here we can see the 3 degree carbocations are getting formed, so this will definitely prefer SN1 reaction and this 1 degree will prefer SN2 reaction and this 2 degree will be in between, right. So either it can go with this one or it can go with this one, it all depends on the reaction condition, what we are using as a solvent, what we have as a substrate and what kind of nucleophile we have. So all the things regarding that decides the reaction mechanism of this 2 degree. But apart from this, if I say we have allylic carbocation like this, here the allylic carbocation is possible, right, here if it breaks. So is it possible for it to undergo SN1 reaction? Yes, it is possible for it to undergo SN1 reaction. So allylic one will also prefer. And if I talk about the benzylic one, so what about this benzylic one? If I say we have this CH2Br over here, so is it possible to undergo SN1 reaction? Yes, definitely it's possible to undergo SN2 reaction, because what happens here, the positive charge will be over here. Now the question is one more thing. If I say over here, now the question is, if here we have positive charge at this CH2, so definitely this positive charge will delocalize in this benzene ring, right? Let's write down it 1 and then you will understand. Here the positive charge will come over here, right? So now the question is, if we have any nucleophile, why this nucleophile won't attack at this position? It is also possible that this nucleophile should attack at this position because the positive charge will be in the ring as well. But the thing is here, the stability. The main factor is what? The main factor is stability over here. Because this is what? Aromatic. So definitely it will be in the aromatic state only. It won't try to get this one. This won't lose its stability from the aromatic to the non-aromatic or the anti-aromatic, right? So this will definitely not try to do this one. I hope you understood about this one, right? So this is the thing which you should understand, and these are the basic things which you know. And one more thing, if I say here, what happens if I take a bridge bicyclo compound like this, where the bridge head carbocations are possible, and here if I say we have this one, so now what will happen over here? Is it possible to undergo SN1 or SN2 reaction? Is it possible? Here positive charge will come. Before it, let's discuss about the Brett's rule, which says that it is not possible to form a double bond, and the first thing double bond, and the second thing is carbocation. It is not possible to form a double bond and a carbocation at the bridge head carbon. Here the carbon is bridge head carbon, this carbon. So it is not possible to have positive charge over here. So this will neither go with SN1 reaction or neither will it will go with SN2 reaction. This may definitely go with other kind of reaction, that may be radical reaction. So it is not possible to go with SN1 or SN2 over here. And the next thing is also here the strain at this, because this carbocation cannot be the planar one as well. So that is also a very important factor over here, right? So that is also one more thing. I hope you understood up to this much. And now let's see some examples, and we should also discuss about the potential energy diagram, right, for this SN1. Let's discuss it over here only, and I think this will be good enough space for you. Let's try to understand. So what is happening over here? In the first step, what we have, if I here what we have here, let's take at potential energy, and here what we take as reaction coordinates. So at the first step we have this substrate. So let's say our substrate is at this position, and after that it is forming a carbocation. So its activation energy is increasing, right? And then the formation of carbocation takes place at this position, and after this what is happening, the weak nucleophile is attacking at this carbocation, and again its potential energy will increase, and that is going to form the product. So here we have this product, and here we have this substrate, and here what we have, here we have the intermediate, and we have already discussed about the intermediates, reactive intermediates, right? So in that we have discussed in detail about the carbocations and all. So here we will have this one. So this is the potential energy diagram, and the thing what we were discussing, the activation energy at this step, the activation energy at this step, it totally depends on the stability of the carbocation. If the stability of the carbocation will be high, then in that case activation energy will be low, right? Because that won't require much energy to get converted into the carbocation. I hope you understood up to this much, right? And now let's discuss little more about this one. SN1 and SN2. So the thing is, if I say we have something like this, we have compound something like this over here. Now if I ask you whether it will go under SN1 reaction or SN2 reaction, what will be your answer? So definitely you will say that you can get actually little bit confused over here. Why? The reason is here we are using this Cn minus, which is not a very strong nucleophile, right? This is the weaker one, and also it all depends on the what kind of solvents we are using over here, right? So here the possible product which we will have over here is this one, and the thing is this can also undergo either SN1 or SN2 reaction. It all depends on the reaction condition. Here because we are using this Cn minus nucleophile, which is quite actually weaker one, so you can say this will be SN1 type of reaction. So this is the second thing, right? Now if I talk about the, here we have something like this. Here if I talk, we have something like this, right? And here what is this? This is what? This is the metal, actually metal halides. This is the metal halides or the metal salts, you can say. So here if we have something like this, so what happens? This actually promotes the formation of carbocation. So here it will be quite easy to form the carbocations over here. I can write C over here, and I can write let me write C, only C over here, right? So it is very easy to form this one, and this MXN, and this X will produce this one. For example, let's say if we have this MXN as AlCl3, which is a Lewis acid. So this Lewis acid will definitely promote the formation of this carbocation, right? So this AlCl3 will coordinate with this one, and that is going to form AlCl4 minus, and the formation of carbocations will be promoted over here. So I hope you understood this one concept as well, right? Clear? Now the thing is, if I say we have a reaction, and if I say whether that is SN1 or SN2, let's find out. If I say we have something like this, here we have R1 and R2, and here we have this OMe, and here we have this OMe, right? And what is happening over here? If I say we are doing the protonation over here, this question is from the Claydon, right? This is from the Claydon, you can find it over there. So now the thing is, if I say over here we have something like this, so whether it will go SN2 or it will go SN1 reaction, now that is the question actually. So after the protonation, we already know that this H plus will actually being attacked, this H plus will be attracted by this one, and the formation of something like this will take place, and here we will have this OMe, and here we will have this OMe, and H, and this positive charge will come on this one, right? Like this, we will have something like this. Now the thing is, if we have such a crowded carbon over here, so in that case actually this is not possible to undergo SN2 reaction. Now the thing is, you will say that here the next water molecule, in the next step we are using the water molecule. So this water molecule definitely attack at this position, right? So in this case, what you are going to say? In this case, you will say that actually this is undergoing SN2 reaction, right? So once we have such a crowded carbon, where you can see we have this OMe and this OMe, and something like groups are present in this case. So actually the thing is, here this won't undergo SN2 type of reaction, right? So it is not going to promote the SN2 kind of reaction. So it will definitely undergo with SN1 reaction, right? Also the reason is why the SN1 reaction will take place, and if I remove this one, So here what is going to happen? Here we have this R1 and here we have this R2 and here we have this OMe. And recently, if you remember, in the reactive intermediates, we have solved one question regarding the stability of the carbocation. And in that case, we had seen that if a electron donating group is present besides this carbocation, so that is going to stabilize this carbocation by sharing its lone pair, right? So which is making it more stable. So it is a kind of more stable carbocations. So that is the reason why it will undergo with SN1 reaction only. It is not going to undergoing the SN2 reaction, but it is undergoing SN1 reaction. Please remember these kind of examples if you have, right? So that is the thing. So here the product form will be RC1C2 and here we will have this OMe and this OH. So this will be product, but what my question was, what kind of reaction mechanism is possible over here? So that is SN1 kind of reaction mechanism, not SN2 kind of reaction mechanism, because the carbocation which is formed over here, that is stabilized by this oxygen present over here, and that is electron donating group. Now let us also take one more example, and there I should discuss with you regarding this and all. So what happens if, suppose if you are getting something like this, here we have X and Y kind of things present over here, right? So the thing is, actually, if we have, let us say if I am talking about this X and this X and Y, if we have this X as OR and this SR and this NR2 like this, right? So these all things are possible if I add this X, and if it is possible add this Y, like we have this Cl, Br and these I kind of things like OH2, OHR kind of things, if they are at this Y position, so definitely that will prefer SN1 reaction. And what is the reason? The reason is actually the stability of the carbocation. Stability of carbocation, which we already seen over here, because the carbocation which is formed at this place, this will be stabilized with this OR group and this SR group and this NR2 group. So this is the important point which you should remember in this case, right? So I hope it's clear up to till now. Now also we have so many things regarding the so many doubts in this case regarding the SN1 and the SN2 reaction. The thing is, if I see here, the two kind of possibilities there, either the substitution can take place or the elimination can take place, right? Two kind of things are possible over here. So what should be my choice actually? And because in the same reaction you will see that substitution is also possible and the elimination is also possible. So now what I should do and how I can understand? Let's understand.